Hi guys, it's me again, Teacher Jay, and you're here in my video to learn about plotting VLE diagrams. I hope you learned something from this video. Good luck! Okay, so we have here a problem that will require us to plot a VLE diagram, specifically a TXY plot for this mixture. So the problem states that consider the N-hexane 1 and ethanol 2 system at 1 bar. So your component 1 is hexane while your component 2 is ethanol. And the overall system pressure is set at 1 bar. Using Raoult's law, predict the system temperature and vapor phase composition for this mixture and provide a TXY plot for this mixture. So our task is to use the Raoult's law equation to create a TXY plot for this mixture. Compare the results of your modeling with the set of experimental data provided for this system in table P10-18. So we have here already an experimental data for the two substances that are mixed together at 1 bar. So we are going to compare the plot that we generated using Raoult's law and the plot using the data presented here in the question. And then the question is this system properly modeled by Raoult's law? Why or why not? So we are going to see later if the data that we have against the data that we generate from Raoult's law are aligned or not. So let's start it with establishing first the known variables or known information. As you can see here, the only information that is given for the system is 1 bar. So for this one, you have only the only information given is that our pressure is equal to 1 bar. And we cannot proceed with the entire calculation if we do not do mining of data for us to proceed with the next parts of our solution. So we need to recall first the relevant equations for the Raoult's law as well as the Dalton's law. Those equations involved in the creation of our plot. So let us recall first some equations necessary because that's the only given that we have. P equals 1 bar. So we have Raoult's law, which is y1 P is equal to x1 P1 sat, or the vapor pressure of your component 1. You also have y2P, which is equal to x2 P2 sat. And aside from that, we know that the sum of the total equilibrium pressure is also equal to the sum of the products of your liquid mole fraction and your liquid mole fraction for both components 1 and 2, x2 p2 sat. Okay, so there is a hint over here as to how we are going to proceed. We have the equations with us. We only have P is equal to 1 bar as our information. But, as you can see here, we need to know first some equations or some information as to how we can get the vapor pressure of both our ethanol and hexane. Okay, so for this one, what we can do is to search for vapor pressure data pressure data for ethanol. Sorry, I'll just go first with the hexane and ethanol. So that's the next thing that we can do. Of course, from your knowledge in thermodynamics, we can use Antoine equation. I think this is the one of the easiest vapor pressure equations that we can use. So Antoine equation relates vapor pressure to the temperature of the system. So basically, Psat or your vapor pressure is a function of your temperature. Okay. Temperature is a big T. Okay. So usually the data for Antoine equation follows this format. Psat is equal to, log 10 Psat is equal to A minus B over T plus C. So what we only need to find is the data for the coefficients of A, B, and C for both hexane and ethanol. So before I recorded this problem, I already prepared the information related to the vapor pressure of um, hexane and ethanol. So I place it in an Excel file. So as you can see here, I already prepared it. So I'll just paste it here just for us to be, aware and accomplished with that fact. So I have prepared information related to it, and we have to emphasize that for this one, the PSAT that I need to calculate or determine is in bars, while the temperature that I need to use for the Antoine equation to work should be in Kelvin. Okay, so we're now done with that part. So we have information already for that one. The next step that we have to do is to set up the equation for pressure in relation to Psat. Remember that for both the liquid and vapor phase, the relationship holds true that x1 plus x2 is equal to 1 and y1 plus y2 is equal to 1, right? That's always the basic rule for mole fraction. We can actually use this information to simplify our equations for the pressure. So for this one, we have x2 will be equal to 1 over x1, right? So if we have this equation already with us, this one, so basically we have P is equal to x1 P1 sat plus x2, right? But since x2 is already, since we know that from this formula or relationship, x2 is equal to 1 minus x1, we can replace this with 1 minus x1 times p sat, p2 sat. Okay. So how do we proceed for this problem? How do we proceed given that we only have very minor information? Okay, now if we have a known value of 1 bar for this, okay, regardless of the temperature of the system, because the temperature values here will change with depending on the composition, the value of 1 bar should be fixed. Okay, and then the products should be x1 p1 sat plus 1 minus x1 times P2 sat. Your P1 sat and P2 sat are both functions of temperature. So, functions of temperature, right? So, what makes this problem tricky is that you need to choose or probably guess the correct value of temperature so that you can solve for the PSAT for both component 1 and component 2. And once you solve for P1 SAT and P2 SAT, just choose any value of x1. So basically, what you're going to do is to just set this value, okay, and guess for the value of t. So not really guess in a random manner, but perform iteration. Perform iteration in such a way that you are going to determine the correct temperature that will make the entire equation equal to 1 bar. So this is somehow a trial and error process, or you may apply your iteration techniques learned in advanced mathematics or in your programming class, so that you can determine the value of your temperature that will give us a total equilibrium pressure of 1 bar. So I have prepared already the data in Excel, so we are going to demonstrate it later. So now, assuming that you have your temperature with you, so you have to solve it. So solve using Excel. Okay. So once you are done solving for the value of temperature, then we can actually solve for the value of your vapor phase by using the Raoult's law equation. So Raoult's law is again P1, sorry, I think it's not P1. It's PY1 multiplied by X1 P1 sat, right? So for us to determine the Y, we just divide both sides by the total pressure and then multiply x1 and p1 sat and then divide it by the value of your P. Okay, so that's how you get uh, the value of your y1. So actually, the most crucial part here is what? To set for, or after setting this value, the crucial part is this one, the iteration process. Because once you determine the correct temperature at the corresponding mole fraction, then the succeeding value of your y1 will be correct. So that will, the value of your temperature that is obtained after during the iteration, after iteration is done, so we'll determine the correctness of the value of your y1. So that's it. So for the rest of the calculations, I will demonstrate it in Excel to make our lives easier. Okay. So if you are confused as to how we are going to use the Antoine equation, remember that the relevant information there is PSAT. And since this is in logarithmic form, you have to make sure that your PSAT is obtained by getting the um, what do they call this, removing the log by putting everything as a power of 10, or making, yeah, reverting it by converting everything as um, the index of an exponent. So for this one, this becomes 10 to the power of a minus b over e plus c. So this is also another equation that you have to plug in the Excel so that you can plot the diagram. So I think we can now start. So as you can see here, I have prepared a problem already, and then I have encoded as well the table P10-18. So the data here that you can see is the data of P10-18. So we're going to graph that as well later. Okay, so the first thing that you have to do is to set up a value of all your x1s. So, of course, the value of your mole fraction in the liquid phase or all your mole fractions ranges from 0 to 1. So it would be best to prepare it and then, just you can just type it manually from 0 to 1. So what I did is my interval is by 0.05, yeah, until I reach 1.0. So I want it to be, I want the data to be many so that the graph will be more defined. Okay, so next is to you have to guess or you have to solve for the the vapor pressure or the PSAT. I will just change it to PSAT so that we are consistent. Okay, so PSAT and PVAP are just the same. Okay, remember that your PSAT and P1 SAT and P2 SAT are dependent of or it's a function of the temperature. So that's why I have here a column for temperature because this value over here is connected to the equations for our PSAT here. Notice that when I encoded the data for PSAT, the the constant parameters are fixed so that when I attempt to how they call this pull down the cells from this cell, the constants will not be affected by the movement. Okay, so for this one, only the cell AC10, which is this one, is not fixed. Okay, so I have already prepared the formula for P1 SAT and P2 SAT here in the Excel file. And also for the P total, remember that the P total is X1 P1 SAT multiplied by P1 SAT plus X2. X2 is just 1 minus X1, right? And then multiplied by the value of your P2 SAT. So that's the value of your P total. Okay, now notice that I placed here a dummy value of 250 Kelvin. Okay, I need to emphasize Kelvin. So it's not actually the final value, guys, but I just need to place a value because if I don't place a value, the value of your P1 SAT and P2 SAT will produce a weird value. So I just put there a dummy value for temperature. So how do we do this? Our goal is for us to have a P total of 1, right? And we need to look for the correct value of temperature to achieve the correct value of P, which is 1. Okay, so what I'm going to do here is I'm going to use an iteration tool in Excel. It's a very simple iteration tool and it's already here in your Excel. We have here what if analysis, and you click here the goal seek tool. So again, you click this area over here, like the P total that you want to become 1 bar, and then the what if analysis, you go to the data, click what if analysis, and then click goal seek. For the goal seek, the purpose of the goal seek is for us to achieve a certain goal by varying another cell. Okay, so our goal here is for this cell over here that I highlighted, which is AF10, to be equal to 1 because that's the total pressure, right? That's 1 bar. And we need to change the value of your temperature, which is this cell over here, so that your P total will become 1. So basically, this is an easy way for us to iterate the values without without using other complicated techniques. So if I click OK, watch what will happen. So the computer will do computations again and again so that we are going to, or we can reach the goal of achieving 1 bar. So in this case, it only achieves 0.999, which is totally fine. Yeah, I think that's okay for me. Then notice that your P1 sat and P2 sat changed. And then from 250, your final temperature becomes 351.10. Okay, so I will be dragging this one so that the rest will um, do the same thing, and I will also drag the P total. So what you're going to do for the entire duration is to change this cells over here in this column for P total in such a way that your P total will become 1, and then the value of your temperature will change to the correct value. So you have to do this for each of the cells. So starting from this one, I already did this. You do the same thing for the others until you reach this point. So this will be somehow lengthy, but only for the part that you are going to iterate each cell. So let's start for the second cell. So we have a click here, another goal seek. You need to set the cell, this one, to value 1 because our total pressure is 1 bar. And then we need to change the cell to 50. To 50 is just a dummy value. Okay. And then the final answer is 350.25. Okay. So we are going to do that over and over until we reach this part here, the last one. So, okay, I will demonstrate for the third time. Click this one and then do value 1 bar, and then you change the cell here, temperature. Okay, so there. So notice that the total pressure
The formula
becomes
for
1 bar.
y1 is equal
Okay,
to
now for the value of
this
the
one.
vapor phase
Okay,
y1,
y1 equals x1
I
p1
think I
sat
have
over
already
p.
prepared
So
here
that's
the
what I placed
formula.
here in the Excel
So
file.
the formula for
So you have to
y1,
make sure
you,
that the correct cells are encoded for the value of y1. Okay, so yeah, I just dragged it down, and then that's the correct value of my y1. So you just drag it down once all the values of your p are already correct. So you need to correct all of them, but yeah. Okay, for what I did actually before I presented and recorded this video, I already um, calculated all the values of the temperature for all the set values of x1. So what I'm going to do here is I will just copy paste all the values of temperature to the correct column. Okay, there. And then, but for your part, I think you need to try to calculate them one by one so that you can really try how to do it. Okay, so as you can see here, copying the correct value of P will change the value of your P. So all of the values of your P are now equal to 1. So you can now then drag the formula for the value of y, and then you have your correct equilibrium mole fractions of the vapor phase for your n-hexane. Okay, so you're now done calculating the equilibrium data. So at this point, I'm now organizing the data I calculated. Okay, so we can actually highlight the values over here because these are the data points that will be essential for us to create the TXY plots. Okay. Yeah, you can actually create an XY plot here because you have the X and Y plots with you. And remember that XY plots are, um, how do you call this? Created at constant pressure. Okay, so to create a TXY plot, okay, so we can start it with going to here. Yeah, here insert and then insert scatter plot. Select data. Okay, so you click the select data and then you click add. For this one, we're going to type here the name of, so we're going to make two. So TX and TY plots. So for the TX plot, your X value is the liquid mole fraction of your N-hexane and your Y axis is your T. Okay, so you click OK. So as you can see here that this is your TX plot. So the Y axis is the temperature, okay, of the system, and then the X axis is the mole fraction. Notice that the mole fraction has an extra value of 1.2, but we only have up until 1.0 because that's the maximum mole fraction. So to edit this, we can edit this, remove the 1.2. So you click the y-axis and then right click format axis and then change the value of 1.2 to 1.0. Okay, so that changes the value of your x-axis from 0 to 1.0. Okay, next is you click again the okay, let's delete this one. You click again the scatter plot and then click select data because we're going to put again we're going to put now the TY, so the equilibrium vapor. So you type in here the TY, okay, TY, and then the X values will be your Y1 data, okay, and then your Y values will be again your system temperature. Okay, so you now have the two curves. The blue one is the bubble point curve, while the orange one is the dew point curve. So we're going to make this look pretty, okay, to make it look usable by doing the following. So for this one, you can click the data and then okay, click the entire data. Make sure all of them are highlighted. Okay, so you do a right click. Okay, oops. Okay, let's click this one first. Okay, right click. Okay, format data series. Okay, format data series. And then let's remove or let's add first lines. So the line here should be solid. And then the color should be matched with the markers. So I decided to color it blue. You can color it any color you want. And then for the markers, yeah, for the markers you can change it to none so that you can only see pure lines. Okay, there. And then let's also edit the other one. Okay, so yeah. For the other one, you click Format Data Series, and then, okay, so you add lines. So it should be solid line. So the color, I decided it to be orange. You can choose any color as long as I would encourage you to make the lines have different colors to make it distinguishable. And then remove the um, okay. And then after that, you add the axis names. So the y-axis is the temperature of the mixture, and then the bottom part is the mole fraction of n-hexane. It can be liquid mole fraction or vapor mole fraction, so you add x or y. Okay, that's it for your TXY diagram. Okay, you can we can actually create an XY diagram for this one. So let's create another scatter plot. Okay, so the new scatter plot. Okay, so the first data that we're going to create is the equilibrium line. So the equilibrium line contains your liquid mole fraction as the x-axis. Okay, so this will be your x-axis, while your y-axis will be the vapor mole fraction. Okay, there. So, okay. So, okay. So, the curve that you will be forming afterwards is the equilibrium line. Let's edit the axis, make the maximum to only 1. Okay. So let's not forget the y-axis as well, because both the x and y-axis are mole fractions. Okay, it's different for txy. Okay, so yeah, that's it for your equilibrium line, but it's not yet usable because we don't have yet the 45-degree line. Okay. Yeah, so but before that, we need to make the scatter plot into a solid line, or let's add first for the 45-degree line first. For the 45-degree line, the 45-degree line just simply means y equals x, right? For any value of y, the value of x should be the same. So for that one, you just choose any of the data points, either the liquid mole fraction or the vapor mole fraction. For my case, I chose the liquid mole fraction. Okay, for the values of your x and y axis, it should be the same, so that it can create a straight diagonal line. Okay, so the 45-degree line is just equal to y equals x. So just choose any value sa x mole fraction or y mole fraction. Okay, I make it sure here in this part that the 45-degree line is not that really highlighted, because it doesn't actually have any bearing in terms of the equilibrium data. It's just there as a guide for the chemical engineering design soon, which is the design of um, distillation columns. So that's the purpose of the equilibrium line. Okay, so there. Okay, so that's the blue line is your XY plot. And then let's add here the axis titles. So the y-axis is the equilibrium vapor mole fraction of n-hexane, while the x-axis is the equilibrium liquid mole fraction of n-hexane. So you only show the more volatile component, okay, which is n-hexane. Is n-hexane the more volatile? Yeah, I think so. Okay. So at this point, let's now add the data given in the problem. Let's now compare it with the Raoult's law data. So this experimental data is obtained from experiment, and we'll see if the experimental data follows Raoult's law. Okay, so let's add again. Since this is a TXY diagram, so let's add two more. TX experimental and TY experimental. So you just follow the same thing as what we did. So you add TX. So your X value is the liquid mole fraction, the X-axis, and the Y-axis is your temperature. Okay. Okay, and then you add another data set. Okay, TY experimental. Okay. So your x-axis is your y1, and then your y-axis is your temperature. So there. So as you can see here, the experimental data does not match or conform with the Raoult's law assumption that we had. So our experimental data is actually behaving non-ideally, and it actually has a low temperature boiling point azeotrope. Yeah. Okay, so yeah, so I hope you were able to apply what you've learned in the discussion here. So it also has a boiling point azeotrope at a composition of, I think, around 0.06 here, there. Okay, let's highlight it. Okay, so at that temperature and composition, there's a boiling point azeotrope. So it boils at that certain azeotrope composition, and then you cannot separate both the liquid and vapor phase because it's there's no use in separating because the compositions for the vapor and liquid phase for the two components are just the same at that point. Okay, so the answer is no, it doesn't fit the Raoult's law. So I hope you now learn how to plot pxy and xy. The same principle is true for pxy. Pxy diagrams are way easier than pxy because in pxy, you just need to maintain the temperature constant. So it's not difficult in terms of using the Antoine equation. Okay, so I hope you learned something from this video, and yeah, by now you now know how to plot VLE diagrams. Okay, thank you so much, and see you in my next video.